In this video, we're going to estimate a multiple linear regression model. We're given again data for the 3C Corporation. In addition to having information regarding overhead cost for 24 months and repair hours for 24 months, we now have 24 months of information related to the direct labor hours. And we're going to estimate a multiple linear regression model including both independent variables. But first, we're going to estimate the slope, intercept, and R-square with Excel functions for both repair hours and direct labor hours as if we were using a simple linear regression model. We'll begin by estimating the intercept for repair hours. Remember, equals intercept, and at this point in time we can highlight directly our known y's, which again we're estimating the overhead cost, and comma the known x's, which is our independent variable, repair hours. And we could copy that or hit enter, but instead we are going to go ahead and anchor the cell references for the overhead costs. So we can copy this column directly over. We can enter dollar signs directly, or hitting the F4 key will toggle between having dollar signs and not having dollar signs. We want absolute references for the data in column E. For the slope, equals SLOPE, and again we can come up and hit the FX to pop up the function wizard, and that way we can highlight directly our overhead costs and now our repair hours, our known X's, and hit OK. Again, however, I want to make sure I've anchored my cell references to overhead costs so I can copy this column across for direct labor hours. By anchoring properly, I can highlight the cells and copy them directly across. To do that, highlight, line the crosshairs up on the lower right-hand corner, and drag it across. One of the first things we notice is that direct labor hours have a greater explanatory power than repair hours. Direct labor hours explain 62.9% of the variability in overhead cost, whereas repair hours, from the last video and exercise, we find only explain 22% of the variability. Let's go ahead and answer some questions. The first is the question we just observed, and that was how much of the variability in overhead cost can be explained by variability in repair hours, and again, that's given by the R-squared, 22%. How much of the variability in overhead cost can be explained by the variability in direct labor hours, and that's 62.9%. So on an individual basis, clearly direct labor hours does a better job at predicting our overhead cost. Let's now go ahead and use Excel's data analysis tool and run a multiple linear regression model using all 24 months of data. And again, be sure we're going to select labels and print our output to cell C60. So we go up top, data, data analysis, regression, we input the Y range, and again, the Y range is our dependent variable. We're trying to predict overhead cost. Again, I included the label row up in row 9, and our input range, repair hours, and direct labor hours. And I've got labels, and I'm going to put my output. We've been instructed to put it in cell C60. By the way, just for your further information, when you're selecting a range for your independent variables, they need to be continuous. We can't select one range, hold the control key, and select another range. They need to be right next to each other. So again, C60 is where I wanted to put my output, and we'll hit OK. Let's answer some questions using our output. How much of the variability in overhead costs can be explained in the combined model using repair hours and direct labor hours? Again, that's our R-squared, 64.7% or 64.8%. What's our slope coefficient for repair hours in our multiple linear regression model? That's 2.23. What's our standard error? That's 2.12, and we could calculate the t-stat, recall, by taking our slope coefficient and dividing it by our standard error, 1.05, or we can pick it up directly using a cell reference. And our p-value is 30.5%. And we'll talk about that 30.5% in a minute. Let's pick up the information for direct labor hours. Our slope coefficient, 68.31. Standard error, 13. And again, we can calculate our t-stat by taking the slope coefficient, estimated b, divided by the standard deviation, or standard error, and we get 5.05. Or we can pick it up directly from our regression output. And then finally, the related p-value, which you notice is essentially what? 0. Which variable is more significant in our multiple linear regression model? If we look at the t-stats and the p-values, because they essentially tell us the same thing, the more significant variable is direct labor hours. It has a higher t-statistic, which of course corresponds to a lower p-value. So in our multiple linear regression model, it is direct labor hours. And that, of course, was the same result we found up above in row 42 for our simple linear regression model. And that's not surprising. We would expect a variable that shows stronger relationship with our overhead costs in a simple model would probably also have more explanatory power in a combined model. That won't always be the case, but typically is. Let's go ahead and talk for a few minutes about our larger R-square for our multiple linear regression model. Our R-square for our simple linear regression model, only using direct labor hours, would have been 62.9%. If we look at our regression output, we can pick up something referred to as our adjusted R-square for our multiple linear regression model. And our adjusted R-square appears right below our regular R-square. And in this case is 61.4%. What's important to notice is that whenever we add additional variables into our regression model, the R-square will increase. This is just a mathematical fact. I'm going to ask you to try it on your own on the next worksheet tab. Make up a third completely random variable and rerun the regression. You will observe an increase in the model's R-square. But of course, adding completely random variables to our model does not necessarily give us a better predictive model. And if we look at an individual's variable's t-stat or p-value, we will see this. And we can also look at the adjusted R-square. And if our adjusted R-square is lower than the regular R-square without the variable, then we probably shouldn't include the variable in our final model. What was the p-value for repair hours in our multiple linear regression model? And again, we just calculated that. And that p-value is 30.5%, which means that there's probably basically exactly what it says, a 30.5% chance that there really is no relationship between repair hours and total overhead cost. That is, the null hypothesis, b equals 0, is true. And again, that's despite our estimate using our data that it's 2.23. But again, a pretty big standard error relative to our slope coefficient, which is why we had the low t-stat and the high p-value. Likelihood is there really is no relationship. We'll talk about this in a second when we talk about our confidence intervals. And the question is, if we set a 10% confidence level, in other words, an alpha of 10% for making a type 1 error, should we reject the null hypothesis that the true slope coefficient is 0, that it's not our estimate of 2.23, but rather it's 0? What exactly are we talking about? A 10% confidence interval, recall, means that we are at most willing to incorrectly reject the null hypothesis 10% of the time. And a p-value of 30.5% means that based on our data, if we accept that b is 2.23 rather than really being 0, we have a 30.5% chance of being wrong. And this is more than the 10% chance that we're willing to accept our 10% alpha. Therefore, we want to fail to reject the null hypothesis. We don't accept that it is true. We don't use that wording. We fail to reject that beta is 0. Let's make one more observation. What was our estimated slope coefficient for repair hours in our simple linear regression model based on the prior worksheet tab? Or we could have picked the value up from above, but it was 6.897. So let's link to that or the value up top on the current worksheet tab. And we can see that this 6.9 estimate for our slope coefficient is very different than the 2.23 in our multiple linear regression model. Let's also pick up the p-value that we had for repair hours in our simple linear regression model. And that was 0.02091, or 2.1%. Interesting. Last time we had a higher slope coefficient and we had a lot more confidence in it. Why is that the case? This brings up two important points or observations. First, in the absence of other information, direct labor hours, repair hours is forced to explain all of the variation in overhead costs. So again, in the absence of that other information, the new information about direct labor hours, we had to try to use repair hours to explain all the variation in overhead costs. But once we've added an additional explanatory variable, direct labor hours in this case, there isn't as much information left to explain, and we observe a considerably different estimated slope coefficient, 6.9 versus the 2.23. The second thing we observe is that in the absence of other, and in this case better information provided by direct labor hours, repair hours provided some information for predicting our overhead costs. And we had a 2.1% p-value. But once we added direct labor hours as a source of information for predicting overhead costs, repair hours isn't very important. It adds very little additional information, hence the 3.5% p-value. Consider the use of high school GPA and SAT scores to predict college performance. High school GPA by itself provides us some useful information, but once we know a student's SAT score, knowing their high school GPA just isn't quite as important. We find this same thing true with repair hours. In a model by itself, it had a p-value of 2.1%. And if our confidence level was 10%, we certainly would have included repair hours in our model. But once we've introduced direct labor hours into our model, and recall direct labor hours did a good job explaining, there wasn't a lot left for repair hours to explain. And we saw a p-value of 30.5%. And with a 30.5% p-value, at most any confidence level, but certainly a 10% confidence level, we're going to reject the hypothesis that the slope coefficient is different than 0. And so we don't want to use a model that will include both direct labor hours as well as repair hours. But for the sake of an argument and exercise, if we use our multiple linear regression model, what is our estimated overhead cost for 400 repair hours and 80 direct labor hours? Let's just link to our data. Our intercept, 4,115 plus 2.2 times 400 repair hours plus 68.31 times 40, or was it 80 direct labor hours. In our next video, we're going to take a look at something called multicollinearity and things that we need to keep an eye out for when we're using multiple linear regression.